Let's prove theorem 122, which was stated last time. So if n and m are natural numbers, we will show that n has cardinality less than or equal to m, if and only if n as a natural number is less than or equal to m. Remember, this less than or equal to has to do with the ordering that we built, sort of using membership and next, when we constructed natural numbers. So this is inherent to the way in which natural numbers are ordered. On the other hand, this sort of curvy looking less than or equal to symbol refers to the existence of an injection and doesn't necessarily have anything to do with natural numbers. You could use this to describe a relationship between any two sets. Okay. So let's start with the easier direction, since it's nice to get that out of the way. So let's assume that n is less than or equal to m. Actually, I guess I should start with let n and m be natural numbers. And then we'll start with this direction. So assume n is less than or equal to m. Then, can we prove this? Can we prove that there exists an injection from n to m? So how do I prove there exists an injection from n to m? I must find one somehow. Find one that's been produced by some other theorem, or find one that I've constructed myself. So the task is to find or construct an injection from n to m. Let's think about what happens for small numbers. So sometimes if you're stuck, it does help to look at an example and see what features of your example can generalize. So for example, 0 is less than or equal to 1. Is there an injection from 0 to 1? Well, 0 is the empty set. Yeah, there's an injection, but that's a little bit of a weird one to think about. How about 2 and 5? 2 is less than or equal to 5. And I think that 2 is 0, 1. And I think that 5 is the set consisting of 0, 1, 2, 3, 4. And can I think of an injection from here to there? So is there a way to map these guys to these guys, which is 1 to 1, meaning no two things go to the same thing. So yeah, there is. For example, I could try to be creative and send 0 to 2 and 1 to 4 or something like that. But let's be as uncreative as possible so that whatever we do generalizes. Let's send 0 to 0 and 1 to 1. That seems to be an injection, and that there is evidence that 2 is curvy less than or equal to 5, which means nothing more than there exists an injection from 2 to 5. Alright, this is not a proof of any kind, it's just an idea. The idea is that it's because 2 is a subset of 5 that there seems to exist an injection from 2 to 5. And actually, there is an exercise, exercise 139, which is one of the assigned exercises that you should try, where you show that if A is a subset of B, then there exists an injection from A to B. So here, 2 is a subset of 5, and so there was an easy injection from 2 to 5, namely the one that sends things to themselves. Alright, so we'll make use of exercise 139. So if one set is a subset of another, then immediately you can say that there exists an injection. The converse doesn't hold. The existence of an injection from one set to another does not imply that that set is a subset. Okay, so now we have some idea of what to do. Can we prove that since n is less than or equal to m, that n as a set is a subset of m. So now we'd like to think about this. This is something that's not inherent to like the philosophical idea of what natural numbers are, or their essence, but rather it's a particular feature of the construction of natural numbers that we have chosen. So if you think back to when we decided to assign the name 0 and the name 1 and the name 2 and so on to certain objects in our set theory, we more or less arbitrarily chose which objects get those names. As long as they interact with each other, as long as whoever gets those names interact with each other in the right sort of way, things are fine. So this is one of these things that end up working out just because of the particular way in which we defined the natural numbers. And it is convenient. One would hope that no matter how one constructed the natural numbers, with a suitable definition for set cardinality and with a suitable definition of less than or equal to, one would hope that this always works. For us, this is the reason it's going to work, is that when n is less than or equal to n, n ends up being a subset of n. So what justifies this? N is a subset of n. Let's just start proving it and see what's needed. So claim n is a subset of n. Consider anything in the left side and try to prove that it's in the right side. Let k be an n. Then, well, that's another way of saying k is less than n. And that's just because membership is the way we defined less than. Okay, so we're in a situation where k is less than n, and n is less than or equal to n. So by transitivity, which is available to us at this time, because we've proven that, by transitivity, k is less than n. So that's because k less than n and n less than or equal to n. But that's just another way of saying k is in n. Okay, so that's it for this claim. Therefore, by exercise 139, we now know that there exists an injection from n to n. Okay, so that was the easy direction of this. If n is less than or equal to m, then n is a subset of m, therefore there's an injection from n to n. The other direction is harder. Suppose there's an injection from n to n. Can you prove that n must be less than or equal to n? Okay, so let's do that. So to prove the other direction, here's what you might expect would be a good way to start. Again, we're fixing n and m natural numbers, and then assume the left side of this implication. So assume that there is an injection from n to m, and then try to prove that n is less than or equal to m. This is actually not a good way to go. This is going to be really difficult. So an injection from n to m could be a very complicated thing to actually work with. Just any old injection is a very difficult thing to do anything with. So for example, let me show you one of the injections that you could have from 3 to 5. So here's 3, and here's 5. And here's an injection from 3 to 5. You can send 0 to 2, 2 to 4, and 1 to 0. That's one of the many injections that you can have from 3 to 5. Now, of course, we know that 3 is less than or equal to 5. But can you imagine trying to use only the existence of this injection to prove that fact, it's really going to be difficult. Instead, we're going to have to use induction. And even the induction we're going to do is a little bit different and more tricky than previous ones we've done. Previously, when we've had two variables like n and m, and then we've tried to prove something by induction, what we've done is to fix one of the two variables and then do induction on the other one. That's not going to work so well here. So look at what it is that we're going to prove by induction. So I'm not even going to fix n and m at the beginning. I'm not going to fix either of them. Instead, we will prove by induction on m that, and then what I'm writing now is the phi that shows up in our statement of mathematical induction. So we'll prove that for all n, if n is a natural number, then the implication that I want works. So the remaining direction of the proof that we have to do is this implication in this double arrow here. If there's an injection from n to m, then n is less than or equal to n. And we will do this, we will prove that this is true for all natural numbers n. Okay, so I've sort of put the for all natural numbers n quantifier on the outside to make it easier to see the thing that we're proving by induction all on its own. But really the proposition that we're proving is if I want to write out the whole thing symbolically, is this. Maybe I'll use a different color. Is this. We want to prove that for all natural numbers m, the following holds. For all natural numbers n, if there's an injection from n to m, then n is less than or equal to m. So this portion in white chalk, that's the phi for when we do mathematical induction. And the thing we're doing induction on is the m. That's the thing that's going to get replaced by 0 for the base case and by m or next to m, m plus 1 in the induction step. Okay, so you see how this is a little bit different from our previous inductions where two variables are involved, because the phi portion, the thing that we're trying to prove holds for all m, itself has a universal quantifier for all n, where previously what we've had is we've fixed n outside, and then we haven't had this extra quantifier here. This will be important for making the proof work. So if you want, you can try without doing it this way. You can try fixing n beforehand and trying to get the same argument to work and seeing where that goes wrong. That would be a good thing to look at. Okay, so let's start with the base case. Let's state what it is. We want to prove that for all natural numbers n, so I'm writing the phi, but with the m replaced by 0. If there's an injection from n to 0, then n is less than or equal to 0. Okay. Good. Let's prove the base case. So the base case itself is a for all, so I need to prove this for all. So I'll take the universal generalization style of argument. Consider any natural number n, or for short, just let n be a natural number. Then, can I prove this implication? Okay, well, let me assume the left-hand side. Assume there's an injection from n to 0. So, whenever you see this, you should sort of expand it out into what it means. It means there's an f, such that f maps n to 0, and f is injected. So that means we can get an f from n to 0, such that f is injective. Okay, you don't really have to write this part. You can just go from this statement, since it's just by definition this, to the next line here. We can get an injection f from n to 0. We don't know anything about f other than that it is an injection. Its domain is n, and its range is a subset of 0, but hang on, 0 is the empty set. So it sounds like this function's range needs to be a subset of the empty set, so this function's range needs to be the empty set. So, I mean, this is a function, so it's a set of pairs, and every pair has its second coordinate being an element of the range, but the range is the empty set. So it seems like this cannot contain any pairs. In fact, it seems like this is the empty set. So one way to state that in kind of a short series of symbols is, well, here's a general statement first. If G is a function from A to B, then G is a set of pairs with the first entries of all of those pairs being elements of A, and the second entries being elements of B. So this is just always true from the definition of the mapping notation. That if G maps A to B, then G is some subset of the Cartesian product A with B. So in this situation, F is a subset of the Cartesian product N with 0. But 0 is the empty set, so this is the Cartesian product that we're looking at. And if you Cartesian product a set with the empty set, you get the empty set. This was either a theorem or an exercise earlier. And so that means F is a subset of the empty set. But we also have a theorem, the minimality of the empty set, which says when you're a subset of the empty set, you are the empty set. So from this, we conclude F is the empty set. All right, well, N is the domain of F. So now we know exactly what F is. We know everything there is to know about it. N is the domain of F, so we know exactly what N is. N is the domain of the empty set. And the domain of the empty set is the empty set. So N is the empty set. Is that what I wanted? Well, N is a natural number. I wanted to prove N is less than or equal to 0. Well, the empty set is 0. Is 0 less than or equal to 0? Yes, because it is equal, right? Thus, N is less than or equal to 0 because N equals 0. So that's the base case. Here's the setup for the induction step. So we've now finished the base case of the proof of this statement by induction. The phi for our use of the induction theorem is this thing in white, and we are done with the base case. So the induction step is to assume that this holds, with m being some arbitrary natural number, then we must prove that this holds with m plus 1 in place of m. So suppose m is a natural number, and suppose that this thing in white chalk actually holds for m. In other words, assume that whenever a natural number injects into m, that natural number is less than or equal to m. Our goal is to prove the same thing, but with m plus 1 in place of m. So our base case was to prove this for m equals 0, and now we're trying to prove that you get sort of a infinite chain of implications. The 0 case gives you the 1 case, the 1 case gives you the 2 case, and so on. It's basic induction, but the proposition that we're proving by induction is just complicated, that's all. All right, so let me get this straight again. We're assuming that whenever a natural number injects into m, it's less than or equal to m. And I have to prove that whenever a natural number injects into m plus 1, that natural number is less than or equal to m plus 1. So we've got our induction hypothesis here in place. To prove this, we'll follow the universal generalization pattern. Let n be a natural number. And now our goal is to prove this implication. So assume the left side. Assume there exists an injection from n to m plus 1. Remember that m plus 1 is the same as what I've been writing as next m, but now I can write m plus 1 since we have plus available. Okay, this means there's an injection from n to m plus 1, so let's get one. Get f from n to n plus 1 such that f is injective. Alright, now my goal is to prove that n is less than or equal to n plus 1. I am kind of stuck unless I use my induction hypothesis. So I've really got nothing to go off of unless I use this. This tells me if I have an injection from n to m, then I can draw some conclusions from that. Here I have a map from n to m plus 1. Alright. Can I somehow turn this into an injection from n to m? I don't know. Let's look at some examples. So let's go away from the proof for a moment and just consider some examples to see if there's an argument in there that can be generalized. Let's say, so example box, an example situation that we could be in right now is maybe n is 3 and m is 5. Then that means n plus 1 is 6. Okay, so this would be n then. 0, 1, 2, and then m plus 1 would be 6. So this would be 3, this would be 6. 0, 1, 2, 3, 4, 5. And f is a function from here to here. So it maps these elements into these elements, and it's an injection. What could that look like? So let me put down some random looking injection from 3 to 6. So this is f from 3 to 6. So in our example, f maps 3 to 6, maps this set to this set. And it's an injection. So maybe this, maybe 2 goes to 4, something like that. So 0 goes to 1, 1 goes to 0, and 2 goes to 4. So what I mean by this is f of 0 equals 1, f of 1 equals 0, and f of 2 equals 4. To say that it's an injection is just to say that I can never send two things to the same place. So I will never have, for example, f of 0 equals f of 1, or f of 0 equals f of 2. Those will not happen. Okay, so here's something that looks like an injection. The situation that I'm in is that I know, with these example numbers, I know that whenever a natural number can be injected into 5, then that natural number is less than or equal to 5. I want to prove that whenever a natural number can be injected into 6, that natural number is less than or equal to 6. Here's a natural number 3, which is being injected into 6. I want to prove that this natural number is less than or equal to 6. How can I use what I know? How can I use the induction hypothesis? Well, from this picture at least, it looks like this natural number 3 is being injected into 5. It is being injected into 6, but this portion, if I take 6 except for the last position, so if I take the set consisting of just these, that's 5. So when I say this, I mean if you take the curly braces 0, 1, 2, 3, 4 curly brace, that's 5. So it looks like 3 is being injected into 5 here. Even though initially we had an injection 3 to 6, it looks like it's also an injection 3 to 5. Therefore, by the induction hypothesis, 3 is less than or equal to 5. But 5 is less than 6, so by transitivity then 3 is less than or equal to 6, which is what was needed. So that style of argument seems to work anytime 5 is not one of the targets of these pink lines. If 5, the last position here, is itself a target, for example, if I had this, then I couldn't use the argument I just made, because what I have here would be an injection from 3 to 6, which is not any kind of map even from 3 to 5, because 5 would not be a valid codomain. It doesn't contain the range. 5 would be in the range, and so 5 would not contain the range. It's a little confusing, because on the one hand I'm using 5 to refer to the element of 6 named 5, and on the other hand I'm using 5 to refer to the set consisting of 0, 1, 2, 3, and 4. But hopefully that makes some sense. Anyway, what I want you to get out of this example is that it seems to matter whether the last item in this list is actually a target of one of these pink arrows or not. If it's not a target of one of the pink arrows, we have an easy argument that we can make, which is that our injection from here to there can be viewed as an injection from here to, and then this without the last position. Then we can use the induction hypothesis to finish. If the last item is a target of a pink line, then we don't have such an easy argument. We have to do something else. So we will split into cases based on whether the last item is the target of a pink line. In other words, in this example, the question is 5 in the range of f or not? Here, 5 is m. So the question is m in the range of f or not? So we'll split into cases based on that question. Okay, so either, this is kind of excluded middle, either m is in the range of f, or m is not in the range of f. So notice the codomain written here is m plus 1, and we know that the range of f is a subset of this, a subset of m plus 1. M is one of the elements of m plus 1. If that weirds you out to say that, just remember that the less than relation for us is actually membership. So I'm just saying m is less than next m when I say m is an element of m plus 1. So m is one of the things in the codomain, and then I can either have it be in the range or not in the range. Case 1, and this will be the easy case that we can rule out immediately, or deal with immediately. Suppose m is not in the range of f. Then I claim that f is actually a function from n to m. So maybe I should write that as a claim. So I want to show f is a function from n to m. So I already know f is a function due to this mapping statement here. I already know the domain is n due to this mapping statement here, but my claim would be then that the range of f is a subset of m. Then claim the range of f is a subset of m. So to see this is a subset statement, so let's call it k be in the range of f. Then, since the range of f is a subset of m plus 1, k is in m plus 1. So k is less than m plus 1, in other words. M plus 1 is next to m, and we've seen that to be less than next to m is to be less than or equal to m. That was one of our essence of order and succession initial things. Alright, so thus k is less than or equal to m. Now, what I'd like to show that k is an element of m so that I can establish this inclusion. So, in other words, I'd like to show k is less than m. I know k is less than or equal to m, so if k is not equal to m, then I will know it's less than m. Could k equal m? Well, my assumption in this case is that m is not in the range of f. K is in the range of f, so k couldn't be m. One way to think about it is, if k were m, then I would have that m is in the range of f, and m is not in the range of f, which would be a contradiction. So let me frame it like this. Since m is not in the range of f, and k is in the range of f, k is not m. Thus, since k is less than or equal to m and k is not m, k is less than m. I.e., that is, k is in m. So going from k is in the range of f, I reached k is in m. This proves the claim that the range of f is a subset of m. Okay, so hopefully that's convincing that the range of f is a subset of m. Let me erase that and fill in the rest of case 1 here. So then range of f is a subset of m. So we now have that. That was proven, and I erased it just to give myself some room here. So f maps n to m then. So I've got an injection from n to m. Thus, since f is still injective, I haven't changed f, right? It was injective before, it's still injective. Now I'm seeing I have an injection from n to m. So n can be injected into m. There exists an injection from n to m. So this is an existential generalization style of argument. Now I can use the induction hypothesis as planned. N is a natural number, and n has cardinality less than or equal to m, therefore n is less than or equal to m. Thus, by the induction hypothesis, n is less than or equal to m. That wasn't quite the goal. The goal was n is less than or equal to n plus 1, but m is less than n plus 1, so by transitivity, so this is just a statement that m is less than next m, so by transitivity, n is less than, I mean, we actually have that it's less than n plus 1, but let's write less than or equal to n plus 1. All right, so that handles case 1 in our induction step, the case where m is not in the range of f. All right, so I've cleared the, cleaned up the board a little bit, and I've kept the induction hypothesis at the top here, and the thing that we need to prove is this, that whenever a natural number can be injected into m plus 1, it is less than or equal to m plus 1. So I fix a natural number n, assume that it can be injected into m plus 1, get an injection, a specific one, and give it a name f. We're assuming that's injective. And we've already dealt with one case, so the case that m is not in the range of f. Now what if m is in the range of f? Then things are not so simple. Well, if m is in the range of f, then there is something that such that f of that something is m, right? That's what it means to be in the range of f, pretty much. So we should be able to get some, let's call it k, in the domain of f, which is n, such that f of k is m. That's what I get out of m being in the range of f. Now, k is in n, right? That means k is less than n. And I'm only saying it that way just to point out that n is bigger than 0. So n is not 0. Okay, so how am I drawing this conclusion? We know from our theorem about 0, the properties of 0, is that 0 is less than or equal to any given natural number. So 0 is less than or equal to n. It cannot be equal to n. 0 cannot be equal to n because there's something less than n. So if 0 were equal to n, then k would be less than 0. And we also know that can never happen from our properties of 0. Okay, so 0 is definitely less than n. From this, it follows that n has a predecessor. So there's one theorem from earlier about predecessors. N is the next of something. So we can get S such that, not just any S, a natural number S, such that n is S plus 1. N is the next of S. So that was theorem 98, the theorem about predecessors. Okay, so far it's not exactly clear where this is going, but let's just put down an example drawing and let me make it kind of rough. So this set that I'm writing down, this set is n, and if n is S plus 1, then this set goes 0, 1, 2, for its elements, it goes 0, 1, 2, etc., all the way up to S is the last position. And we're talking about maps. I think this diagram is going to get too big. Let me go lower. Okay, so maybe this is n, and this last position here is S. So n is this set of dots, 0, 1, 2, etc., and then there's S. And F maps n to m. Well, actually to m plus 1. And m plus 1 is its own set of dots. 0, 1, 2, 3, and so on, and so on, and so on. And then we've got the dot m over here. Maybe I'll make this look like fewer dots. I don't know why that feels better. And F maps Okay, so this is n plus 1. F maps these dots to these dots, and it does so injectively. So since this is the domain, every dot from here has to go somewhere. And since f is injective, I can never send two dots to the same place. So what might f look like? Well, I'm in the case where m is in the range of f, so that means something got sent to m. So it could be anything. But, yeah, so it could be anything. It could be this, for example. And whatever thing gets sent to m, we're calling that thing k. So that's k. So k is such that f of k is n. And then the rest can go anywhere. So who knows what happens to the rest? You know, here, 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 something like that. Now, I'd like to argue that if s went to m, then our life would be easier. If s went to m, things would be good. So, in other words, if k and s were equal, if s turned out to be the thing we called k here, things would be good. Let me show you why. So, suppose that this were the situation, and then the other dots just did whatever. So then this one wouldn't be k, this one would be named s and k. It would be named s because it's the predecessor of n, and it would be named k because it's the thing that f sends to n. So in this situation, since s goes to n, these don't have to go to the first four things, could go anywhere. But in this situation where s goes to m, what I could do to try to make use of the induction hypothesis is take my mapping from n to n plus 1 and just remove this portion where s is going to n. Then what I have is a mapping from a smaller natural number, because if I take a natural number and I remove the last position, that's another natural number. It's the previous natural number. So I would have a mapping from a smaller natural number to also a smaller natural number. But the point is, the domain is now, or rather, the codomain is now m. So it used to be that the codomain is n plus 1, but if I delete this, the codomain is m, and I'm in a position where I can use my induction hypothesis. So this would be really good if s went to m, because then I can delete this. I have a mapping from a natural number to m, and that lets me use my induction hypothesis. It's still injective if I delete this. Okay, so we don't have that s goes to m, but I'm just trying to show you that we wish we had it. Okay, let's go back to a more general picture, which is more probably what's going on, is that s goes somewhere useless, and someone else goes to m. And whoever it is got called k. And who knows what the other things do? Maybe some random stuff. Okay, but the point is that s is unfortunately not going to m, and k is the thing that's going to m. So what we're going to do is look at we're going to take a function from n to itself, which is bijective and swaps k and s. If we could have swapped k and s, then we could end up in a situation where the last position is going to m. So let me do that a little bit more precisely. We have a theorem, Theorem 121, which I have not mentioned in the lectures, but it's the theorem right before this one, and which you should look at. You should pause and look at it if you haven't. So this theorem says that if I have a set and two elements of the set, then there's a bijection from the set to itself that swaps the two elements. So I'm going to use that theorem. By Theorem 121, we can get a bijection. Let's call it G from n to n, such that G of k is S and G of S is K. So what I'm going to do, okay, so here I've got sort of the mapping. Maybe I should write n here. N is these dots, m plus 1 is these dots. Let me line this up a little better. So n is these dots, m plus 1 is these dots, and f is going n to m plus 1. Then I've got g going n to n. And here's another copy of n. And the way g operates is, I don't know what it does to many things, but I know what it does to k and s. It sends k to s and s to k, so it swaps them. And for the other things, I don't know what it does, but it might as well act like the identity. It doesn't have to, it doesn't really matter. What matters is that it's a bijection, and it swaps k and s. Now if you look at the map, the composite, G followed by F, so we would call that F composed with G, then look at where things go. Here's S and here's K. S goes to K, goes to M. So we're in a situation where S is going to M. Not if we focus on F, but if we focus on F composed with G. So that's the idea. And we need it to be an injection. It is thanks to the fact that G is a bijection. If you compose an injection with a bijection, you get at least an injection. Okay, so that's the idea. We're going to compose these, and then we're going to end up in a situation where when you look at the composite, S is going to M. Then you can pull that trick that I was trying to suggest, where you delete the S to M mapping and leave the rest, and then put yourself in a situation where you can apply the induction hypothesis. All right. So let's see if we can get this to work formally. So the idea is to focus on the composite. So define H to be F composed with G. Okay, now we have our essence of composition theorem, which tells us exactly what kind of thing H is in this situation. Since F maps n to n plus 1, and G maps n to n, H is going to map n to n plus 1. N to n plus 1. Then H maps n to n plus 1. This is really useful. It's packaging a lot of information together. H is a function, the domain is n, and the range is contained in n plus 1. All right. What do I know about H? So the goal from the picture was that H maps S to n. So let's verify that. H of S, well that's F composed with G of S, which is F of G of S. G of S is K, so that's F of K. F of K means M. F of K is M. That was the point of K, is that it's the thing that F sends to M. All right, so H of S is M. So all I'm expressing formally here is what we saw in the picture. H of S is M. H is injective. So why is that? Because H is an injection composed with a bijection. So there's that one theorem. Was it Theorem 95? I don't remember. But it was a homework problem that you probably remember doing, where you show, I think it was 5 things, and one of them is if you compose 2 injections, you get an injection. So G is a bijection, so G is at least an injection. So F composed with G is an injection. So H is injective since F and G are injective. Now, H of S is M. That means H as a set of pairs contains the pair S comma M. It maps S to M, so it contains the pair S comma M. Let J be H with that pair deleted. So remove the pair S comma M. So I'm going to delete this singleton set, delete this one pair. Now if you take an injection and you delete one pair, like this, then you have to go through a bunch of trouble to figure out, to prove for sure that what you get is a function with the domain and codomain that you expect, and that it's still an injection. But all those things are previous exercises, so I'm just going to use them. And you'll see exactly which exercises are being referenced when you look at this in the notes. So what I'm doing is the exact proof that you will see in the notes. So then J maps, let's see, so since I deleted this pair, the domain of H, which was N, gets S deleted from it. And the codomain, M plus 1, gets M deleted from it. Now remember, N is S plus 1, so instead of writing N here, let me write S plus 1. And J is injective. So this whole thing takes a bunch of work, and it does work out by a bunch of exercises. Which you can see the exact ones in the notes. Okay, also there's an exercise that tells you that if you take the natural number S plus 1 and delete S, then you get the natural number S. So this is just another way of writing S, and taking M plus 1 and deleting M, that's another way of writing N. So that is an exercise that you either already did or it's going to be assigned. Okay. And the point was that after we do this, we should be in a good position to apply the induction hypothesis, which it's been so long I forgot what that was. Anytime a natural number injects into M, that natural number is less than or equal to N. Here I have a natural number S injecting into N. J isn't injective, that's why it was important to say that here. So this is kind of an existential generalization. J is an injective function from S to M. Therefore there exists an injective function from S to M. That's what this says. There exists an injective function from S to M. Okay. Now it is, now you can see maybe more clearly than before why we needed to state the thing that we're proving by induction in such a complicated way. Why it needed a for all n here in the phi, the statement that we're proving by induction, rather than fixing n beforehand and then trying to just do induction on m. If we had fixed n beforehand, here we would not be able to use the induction hypothesis, because we ended up with S as the domain rather than n. But due to the fact that we kept this universal quantifier here, we can apply the induction hypothesis because we're applying it to the case in which n, the role of n, is being played by S. So leaving the universal quantifier here gave us a stronger induction hypothesis, which let this proof work. Okay, so S has cardinality less than or equal to m. Therefore, S is less than or equal to m. Thus, finally, by the induction hypothesis, S is less than or equal to m as a natural number. Is that what we needed? We needed n less than or equal to m plus 1, right? But add 1 to both sides of this. We can do that. Why can we do that? So that, let me write it down and then justify it. Therefore, S plus 1 is less than or equal to m plus 1. So where is this coming from? I think it's one of the properties of plus, in that big list of properties of plus. But I think also if you interpret plus 1 as just next S less than or equal to next m, then going from S less than or equal to m to next S less than or equal to next m is one of the early theorems about natural numbers, called something like succession preserves order. Okay, so we've got that, and that's actually what we want. S plus 1 is n, right? That is, n is less than or equal to m plus 1. Okay, so that finishes the proof. There are a few exercises that fill in some gaps. So the major gaps are, well, there's a minor gap, which is knowing that if you take the successor of a natural number, and then delete from it the natural number itself, then you get the predecessor. So s plus 1 delete s is s, m plus 1 delete m is m. And the major gap, which can be filled in by some exercises, is if you take an injection, h, and you delete one of the pairs that is in h, so this is a situation where h of s equals m, and you delete the pair s comma m, then you get another injection, with domain and codomain having the expected deletions also. Alright, so now we know that when a natural number has cardinality less than or equal to that of another natural number, it follows that that natural number is itself less than or equal to the other natural number in the ordering of the natural numbers.